Good morning, everybody. How goes it on this Monday? I almost said Wednesday. Good morning, Michael. Morning, Ryan, Benny, Pat. You guys almost done with all your midterms? One tonight. I mean, almost done doesn't mean that you're done. 7 to 10, a 3-hour midterm. Ooh. So, oh no, don't worry about springing questions this early. So download it from, do not make it a text file. Do not make it a text file. You just can't open it unless you right click and say open with Notepad. So if you're on a Windows, let me download it. Show you what it looks like. Do not make a test file. It needs to be the same file, otherwise I will not be able to work with it. Working project. Okay, download materials.dat, and it should show up in your downloads folder. Delete the parentheses 1. That's annoying. Screen share. So you can't just double click it and open it. That probably will fail for you. You can right click and say edit with Notepad or edit with whatever. You can say open with and find something. You can also just open up Matlab. Which one? Go to downloads in your current folder. And then you can double click and open it in Matlab. Let me show you what that looks like. Let me open up another version of Matlab. But you should just still be able to say, as long as it's in your current folder, you should be able to say load materials.dat. Nope, wrong one. Downloads. Okay, let's stack that. So you can always open it in Matlab, double click it, open it in, never mind. Double click and drag it in. You should be able to see it that way. You can also say load materials.dat, and it should show up in your workspace. But you don't need to actually like open up the folder. You don't need to open up the file and see the values unless you really want to. I mean, I showed you what those values look like. But you can't open it with just your file explorer, whatever you call it, unless you say right click, open with, or edit with, unless you indicate that a .dat file is going to be opened with Notepad++. You can see here I have already previously indicated that, but it's a different file extension, so you just right click, say open with or edit with, find Notepad, text edit, whatever it is, on a Mac. I'm not as well versed on a Mac, so I'm really sorry, those of you guys who have a Mac. But you should be able to open it up in Matlab. Just literally click and drag it into your editor, and you should be able to see the file. Yes, if you just wanted to copy the data into a new file named the same, that also should not break anything as long as it reads in like this table here. Also, if it works on MATLAB Grader, then it will work for me. Okay. Yeah. So there you go. Is it okay if we just copy the data? Yeah, we already answered that one. How do you call information from another function? So, Nick, this is where you have function outputs and function inputs. If you need, so for your analytical function and your, I don't have the project document open right now, otherwise I'd pull it open. But for your part E, I think part E, For part E is where you're going to write a script file that pulls everything together. But if you need, so for your analytical solution and your numerical solution functions, you're going to need an L, you're going to need an E, I, A, all of that fun stuff. So what you do is you call your fork parameter function, call that one first. Notice the outputs for that are going to be F, your frequency, your length, E, I, A, the other one. I'm missing one. But you're going to use those outputs for your inputs for your next function. So essentially you call your fork parameters function, get those inputs, or get those outputs, and then call your analytical solution function with those values. And then you're going to call your numerical solution function with those values as well, and compare them. So in the document it says, for practice, you can use any L value you want, but in the document it says use the first L value in that array. No, you do not use a load function for that. So Michael, has the Matlab graded part for C been fixed? Since remember Friday was passing my code for W, but it shouldn't have. I don't remember. I'm sorry. I don't remember. My brain quit on me on Friday after office hours. So I don't remember. I have 10 emails in my inbox right now from students asking on the project that I haven't gotten to. So if you want to, you can resend me your code and I can check if it works. And if it has the right values. Maybe I did, Ryan. I don't remember. I legitimately don't. I did do something to part C. I just don't remember what it was. So Michael, if you want to just resend me your code, I can check it on my Matlab to see if it works. Okay. So oh my gosh. I legitimately, my brain was not functioning on Friday. Okay. If you did send me an email and I haven't responded to you yet, I am getting there after class today. I am planning on going through those. Okay, let's go ahead and start on the material today. Good questions though, good questions. I really like these questions. So notes. This week, I looked at the responses on the quiz, and half of you guys talked about not understanding the current material, which I gave you a 7-minute video this week. And it's not meant to be comprehensive. That video is not meant to go through everything, and you're not supposed to understand everything. In general, those videos, they're not meant for you to understand everything. They're just meant to introduce the concepts so that when we get to lecture on Twitch, we can just go over examples and talk more about the application of those concepts. So you can stop saying, I don't understand cofactors, I don't understand determinants, because come to class, and that's these videos, class lecture is supposed to reinforce that material, apply that material so that it's a little bit easier to understand and it makes sense. So just as a notice about what those videos are meant to do, they're just introductory concept videos, not meant to be comprehensive for the material. A bunch of other videos a bunch of other things that you guys mentioned were talking about Gauss elimination and GaussJordan elimination and how these problems are long and they're hard, and they are long and they are hard and it is tedious, but these concepts are very important. You need to know how to do row operations because they show up, oh gosh, in at least three and a half of the linear algebra week material. So it's really important that you guys understand how to do row operations. It is long. I gave you guys a lot of examples, and I just want to highlight some of the things in these examples that I didn't get to last week, or that I forgot about talking about last week. So here's an example for Gauss elimination with back substitution. So first things first, you're creating your lower triangle of zeros when it comes to Gauss elimination. That is your first goal. Just do lower triangle of zeros. If anything else shows up, then don't worry about that until you have your lower triangle of zeros. So for this problem here, I'm going to start by making this 2 a 0. So For this problem, I've stepped it out in a little bit more steps. So I multiply row 1 by -2. When I do that, I end up with -2, 12, 8, and 10. So now notice these numbers, -2 and 2, those are the same, but opposite. So when I add those two rows together, remember you have to add rows together. Anything you do has to be across the entire row. So I get 0, 2 minus 2, or -2 plus 2 is 0, 12 plus -10 is 2, 8 plus -9 is -1, 10 plus -4 is 6. Once I have that as a 0, I'm going to get this -1 to be a 0. So to do that, I divide row 1 by -2. So now these two numbers are equal but opposite. These are sum row operations you can do. You can do a different order if you want. It is up to you as long as you end up with your triangle of zeros. Notice when I did this row operation, I ended up with 2 zeros, and that's just a lucky, happy coincidence. So anything else that happens in your row operations, that's fine, not an issue. Your first goal is to get your lower triangle of zeros. Whatever you end up with is where you're going to write your system of equations and work your way, solve for your last unknown, then your second last unknown, and then your first unknown. So the reason why we can do this process is because when we are solving the system of equations, essentially we are using elimination. So just like you've learned previously, we are using elimination. It's just an algorithmic view of elimination. It's a consistent view of elimination where we're not just kind of arbitrarily choosing which unknowns to eliminate. We are systematically trying to get our lower triangle of zeros because we know that that is going to end up with the type of system that we want. Okay, so it's just elimination. It's just a systematic, algorithmic version of elimination where we end up with our lower triangle of zeros. And Gauss elimination can be used with any size system. So if we have a system that looks like this, so here we have 3 equations and 4 unknowns. Generally, if you want to solve for all of your unknowns, you're going to need the same number of equations as you have unknowns. I don't have that in this situation. I have 4 equations, 3 unknowns. I can still set it up as my augmented matrix. These are my A values. This is my B value. AP, that's a really good question. I would recommend you... So for this one, this last equation, no, you don't need to say 1z equals -2. You can just say z equals -2. Like that one clearly shows up. I would encourage you to at least write it out like this. Show that you're actually plugging in -2, because then you're showing us that you know what you're doing. You know that if z is -2, I need to plug it into this equation. And then you don't need to like show all of your algebra if you're comfortable not showing all of your algebra. But at least show us that you know that you're plugging in -2 in for z and plugging in 2 for y. So once again, you showing your work is telling us that you know what you're doing. That's the purpose of your work. So make sure in your work you're showing me that you know what you're doing. Okay, so back to this one. So here we have 3 equations and 4 unknowns. I can still write it in the form of ax equals b. My goal is to still get that lower triangle of zeros. So I put a 0 here first, and then I put a 0 here, and then I put a 0 here. Notice, it doesn't look exactly the way I had before because I don't have a square A matrix, which is fine. I still get my lower triangle of zeros though, and I still write my system of equations. So this one here shows me that x1 plus 2x2 minus x3 plus x4 equals 1. This one here shows me that I have x2 minus x3 plus 3x4 equals 5. And then this one here shows me that I have -3x3 plus 20x4 equals 30. So this is an example where we might have an infinite number of solutions. x4 is this arbitrary parameter that we don't know what x4 is. But if we have a value for x4, if x4 equals 1, I can use it to solve for x3, solve for x2, and solve for x1. So you might run into this scenario where you end up with an infinite number of solutions, but it's still the same process. You still get your lower triangle of zeros. You still write your system of equations. It just so happens that your system of equations isn't going to solve for x1 equals a number, x2 equals a number, x3 equals a number. You're going to have x1 as a function of x4, x2 as a function of x4, x3 as a function of x4. And x4 ends up being, yes, this free parameter, absolutely. It's free. It's whatever, it's any number that's possible. Just given whatever number that is, we can use it to solve for the other unknowns. And we will see what all of this notation means in 2 weeks. So next week, we're going to do more row operations. And we will see what this notation means more in 2 weeks. Okay. But same process, get your lower triangle of zeros. So Pat, you want to graph it. So part 1A2, you are going to draw lines. So y equals mx plus b, solve for your line equation, graph your lines, and plot the intersection point. If you want to solve explicitly for what x and y are going to be, sure, use that as a check, but you want to graph your lines. And then in part 3, or in number 3, then you're going to do the same thing, but with vectors. Okay, so another situation, I'm getting there. For another situation, is you might have a situation like this, where here's a system of equations, you get your first 0, you get your second 0, you get your third 0. You write your system of equations based on this, and you end up with this last scenario, where you have 0x plus 0y plus 0z equals -2. 0 equals -2. That's not possible. That's math breaking. So that means there's something wrong with this system. If you run into a situation where you're trying to break math where 0 equals not 0, that means there's no system, or there's no solution to this system. But the process is still the same. Get your lower triangle of zeros. Go away. Get your lower triangle of zeros, and then write your system of equations and interpret what that means. Okay, and then I gave you a 4x4 system. Gosh, these problems take forever. Note that if you need 1, 2, 3, 4, 5, 6 zeros, that means you should at least be, you should at least have to do 6 row operations. Usually it's about 6 row operations. I'm not going to go over a 4x4 today just because we don't have time, but I do have the examples on UB Learns. And there's videos as well. It's the same process. Find the zeros in your first column. You can always use row 1 to do that. Find the zeros in your second column. Where are they? Zeros in your second column. You can always find, you can always do that using row 2. Find the zeros in your third column. You can always do that using row 3, etc. Okay, GaussJordan elimination. Same thing. It just so happens we're not getting our lower triangle of zeros anymore. We're getting our lower triangle and our upper triangle of zeros. So here is a system where there's just a lot of zeros. So there's not very many unknowns. So there's 4 unknowns, but there's a lot of them are 0. So it's a sparse matrix. It's not truly a sparse matrix in terms of what sparse means linear algebraically, if that's even a word. Algebraically, there we go, that's the word. But we end up with a lot of zeros, which is good or bad. Typically, if there's a lot of zeros, that means that there's less row operations to do. Not always, though. But write it in the form of ax equals b. Notice I have 3 equations, 4 unknowns. That doesn't matter. We're still going to do the same idea. My goal for GaussJordan elimination is to get this to look as close to identity as possible. So here I rearranged rows. Can be useful, cannot be useful. It just depends. Sometimes when you rearrange rows, you work yourself in a circle. But I rearranged rows. And then you get your zeros in your first column, zeros in your second column, zeros in your third column. Keep working your way over. Notice my final result here. This looks like identity, but this does not. Okay, I have this arbitrary column just kind of hanging out. But once again, once you find RREF, once you get it as close as you can to identity, you're going to write your system of equations. This tells you that x1 minus 1/4 x4 equals 0, x2 minus 5/4 x4 equals 0, x3 minus 3/4 x4 equals 0. Once again, we have that infinite number of solutions. x4 is our free parameter. We don't know what x4 is, but given x4, I can solve for x1, x2, and x3. So for Gauss elimination, get your lower triangle of zeros, write your system of equations, interpret it. Same thing for GaussJordan elimination. It just so happens we have our identity. We're getting it as close as we can to identity. So here's another example. 0 here, 0 here, 0 here, 0 here. Get your first column of zeros, get your second column of zeros, get your third column of zeros. I don't know why that one's highlighted. Probably an accident. And this one here, we can easily see what the solution is. Yes, so here's a 4x4 example for Gauss-Jordan elimination. This one took me forever to type up because these are the longest, most annoying problems. There's not, it's just multiplication, it's just addition, but there's a lot of things going on. So it's very important that you show all of your work, that you're being careful about misplacing signs, because you can make one small mistake and it can just ruin the entire problem. I think I initially typed this as like a -15. I did my math wrong, and I sat there debugging this problem forever. I'm sitting there with Matlab, I'm doing my row operations one at a time, double checking my matrix because I was not getting the right answer. So these problems, they can be very, 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 very long, very, very annoying. But in general, you want to get your zeros in your first column first. You can always do that using row 1. So make this a 0, make this a 0, make this a 0. Once you have column 1 done, move on to column 2. You can always use row 2 in order to do that. So make this a 0, make this a 0, make this a 0. Once you've done that, move on to row 3. Or column 3. You can always use row 3 in order to do that. So this is 0, this is 0, and this is 0. And then move on to your last row. Or however many columns, your last column, however many columns you have. There we go. End up with your identity. Notice how many row operations this one took. This one took forever. Okay, how would you check your answers in MATLAB? So if you want to check your final answer in MATLAB, you can use RREF. So if you go to MATLAB, you have your A matrix, or your augmented matrix. Let's pretend it looks like this. Let's pretend it looks like that. You can say RREF, and then whatever your matrix is, and it will give you what your answer is. If you want in fractions, you can say format rat, and then do it again. And it will give you your fractions. There we go, it will give you your fractions. If you are doing Gauss elimination, then you can really just check your final answers. When I say I was checking my answers in MATLAB, I was legitimately saying, okay, column 3 is going to be column 3 plus 5 times column 2, or row 2, A2. Yeah. So I was legitimately going through and doing each row operation one at a time on my matrix by redoing it, which can be very tedious and very obnoxious. Okay, those are the things I wanted to go over with Gauss elimination and Gauss-Jordan elimination. So make sure you get your lower triangle of zeros. Write your system of equations that results from it, interpret that. Same thing for Gauss-Jordan elimination. Get your lower triangle of zeros, get your upper triangle of zeros. Get it as close to identity as possible. Write your system of equations that result from it. Most of the time, it's going to be simple, where it's going to be x1 equals -1, x2 equals 3, x3 equals 2. Most of the time, that's what it's going to be. However, not all the time if you have no solution or an infinite number of solutions. Okay, and we will go over this a little bit more in 2 weeks as well. Okay, let's move on to this week's material. Notes. So this week's material is all about determinants, which are fine. It's a little bit easier than row operations. there's just less going on. I find it a nice reprieve from row operations. But essentially, in the video, we talked about determinants. We talked about we introduced this idea of cofactors. But we've already seen this material before. We saw this with 2x2s. We know how to calculate the inverse of a matrix for a 2x2. We know how to do the determinant of a matrix for a 2x2, and all of that fun stuff. So this week, we are expanding it to a 3x3 and a 4x4 and 5x5, etc. When we are talking about determinants, though, we are always talking about square matrices. So it has to be square. So the determinant for any size matrix can be calculated using what's called cofactor expansion. A cofactor is just another determinant. So we're going to be calculating determinants on determinants upon determinants for this chapter, which is fine. Determinants do tend to be relatively easy. Once again, there's a lot of multiplication, a lot of signs. We can make a small minor mistake, but it's typically not as detrimental as it is for our Gauss elimination or GaussJordan elimination. So our process for finding cofactors and finding determinants is listed out here. I didn't go over this in the video because we're going to go over it in class. So let's talk about cofactors first. So cofactors are these fun things that show up over and over again in linear algebra. So let's look at this matrix. It turns out every single number in a matrix has what's called a cofactor. So the process to find cofactors is listed out here. So first thing we're going to do is we are going to pick an element in our matrix. We are going to remove the row and column of that element. We are going to calculate the determinant of the remaining values in that matrix. So a cofactor is just another determinant. And then we're going to adjust the sign based on this grid. This grid always starts at a positive in the upper left, and then it alternates negative, positive, moving down and across. So let's look at examples. So let's pick this number here. If I want to find the cofactor for this number, so C11, the cofactor for the row 1, column 1, first thing I'm going to do, I'm going to remove the row and column it's in. So I'm going to move my row, remove my column, and then find the determinant of my remaining elements. 5, 5, 5, 5. If you remember, the determinant for a 2x2, I just draw my little fish, it's going to be 5 times 5 minus 5 times 5. Or in this instance, it's going to be equal to 0. So 5 times 5 minus 5 times 5. Now I need to adjust the sign based on my grid. I'm going to draw my grid down here. It starts at a plus in the upper left. And then it alternates positive, negative, going across and going down. So for this 1 here, this 1, 1 location, that corresponds to a positive. So there's my plus. So this is a positive 0. That is my first cofactor. My cofactor for this 1, 1 element. Okay, so let's find another cofactor. Let's look at the cofactor for this one. C12, row 1, column 2. Same thing. I remove the row and the column it's in. The remaining elements I find the determinant of the remaining elements. So -4, -2, 5, 5. So it's -4 times 5 minus -2 times 5. Or -20 plus 10, or -10. Change the sign. For the 1, 2 location, it's a negative. So it's -10 or +10. And then I can keep going. So if I want to find the cofactor for the -4, C13, remove the row and column it's in. My remaining elements are going to be -4, -2, 5, and 5. -4 times 5 minus -2 times 5. That is going to be -10, because it's the same as the one above. The sign for that same location is a positive. So it's a positive -10, or just -10. And I can do this for any element in my matrix. Let's say I want to do it for this 5 here. So 2, 3. Row 2, 3, 2. Sorry, 3, 2. Row 3, column 2. I'm going to remove the row and column it's in. My remaining elements are going to be 1, -4, -4, 5. 1 times 5 minus -4 times -4 equals 5 minus 16, or -11. The sign in that same location is a negative. So I have a -11 or a +11. So we can find the cofactor for every single element in our matrix. So that's a cofactor. Okay, that's nice. That's fine and dandy. Why do we care? Come on. There we go. So it turns out cofactors show up a couple different times. They show up in calculating determinants. They'll also show up in calculating the inverse of a matrix, which is the easier way, or at least in my opinion, the easier way to do it. No, I spilled. Great. That's fun. Give me a second. There we go. So like I said, we can use cofactors in order to calculate determinants using something called Cofactor Expansion. And this works for any size matrix. So this works for a 3x3, a 4x4, 5x5, any size matrix. So what we're going to do is we are going to choose a single row or a single column in our matrix. Choose a single row or a single column. Doesn't matter, as long as it's just one of them. Then what we're going to do is we are going to, for each element in that row or column, we are going to find the cofactors. Once we find the cofactors, we're going to multiply the element by its cofactor and add it together. This is called Cofactor Expansion. So let's look at an example. So I'm going to find the determinant of this matrix here using Cofactor Expansion. So first thing I do is I pick a row or a column. In general, just a strategy, you pick the one with the most zeros, because you'll see why. I'm going to pick row 1. If there's really no advantage to any single one, I typically pick row 1. Doesn't really matter. We just pick one. So what I'm going to do is I'm going to find the cofactor for each of these elements. Find the cofactor for 1. We already did that. It's 0. Find the cofactor for this one. We already did that. It's 10. Find the cofactor for this one. We already did that. It's -10. Once you find all the cofactors, you're going to take the numbers in your row or column, whichever one you chose, multiply it by the cofactor and add together. So I'm going to take 1 times 0 plus 1 times 10 plus -4 times -10. Add that all together. I get 0 plus 10 plus 40 equals 50. So the determinant of A is going to be 50. There we go. I found the determinant of my 3x3 using Cofactor Expansion along row 1. Let's do it again. Let's do it the same thing, find the determinant, but I want to do it now using column 2, just for kicks and giggles. Let's say I chose column 2. I do the same thing. I'm going to find my cofactor for the 1, 1, or for the 1. So C1, 2 is going to be, so for this column, my determinant, remove the row, remove the column. I'm left with -4, -2, 5, and 5. This gives me -20 minus -10, or -10. My sign for that number is a minus. So this becomes +10. I already did that one. Yeah, so we should get the same answer using this row, or using this column. So moving on to my next one with the 5, C2, 2. I should get 1, -2, -4, 5. Or it's going to be 5 minus 8. The sign for that one is a plus, so I'm going to end up with -3. And then keep moving. For this one, remove the row, remove the column. I get 1, -4, -4, 5, or 5 minus 16. And the sign here is a minus, so I end up with -11, which converts to +11. So then I'm going to take each number in my column, multiply it by its corresponding cofactor, and add it all together. I should get 50, just like I got using row 1. So 1 times 10 plus 5 times -3 plus 5 times -11 gives me 10 minus 15 minus 55 gives me negative. That's a +11. +11. Positive 55. So I get a -5 plus 55 equals 50. So it works. It should work. You should get the same answer regardless of which row or which column you use. Okay, so let's go ahead and check it for a bigger one. So let's say we want to do it for a 4x4. The process is still the same. I'm going to pick a row or a column. In general, you want to pick the row or column with the most zeros. Because if you have a 0 there, it doesn't matter what the cofactor is. It's going to end up being 0. So for this one, I'm going to pick row or column 1, just because it's easier. And I'm still going to find the cofactor for each element in my column. So the cofactor for this one here, I really don't care. It doesn't matter. It's going to end up being canceled out anyway with my 0. And cofactor for this one, same thing. I don't really care because it has a 0 there. It's going to be multiplied by 0, which is awesome. So now this one. So my cofactor is going to be remove a row, remove the column. It's going to be the determinant of my remaining matrix. Okay, that's a 3x3. So it's a little bit harder to calculate. Or I should say it's not harder to calculate. There's just more work to calculate the determinant of 3x3, but that's okay. I know how to do it. The sign for this column is plus, minus, plus, minus. So this overall sign here is going to be a plus. Okay, so the determinant of this matrix, it's going to be, once again, I can use cofactor expansion. I can use any row or column I want. I'm going to use row 1 just because it's my default row to use. So plus, minus, plus. So plus 2 times -3, 3, 1, 2. Then I have my minus -2 times the determinant of -2, 1, 1, 2. Plus -1 times my determinant, -2, 1, -3, 3. So here I'm showing all of my steps at once. You can still write it out individually. The more comfortable you are, the more problems you do, you'll be more comfortable writing it all at once. Notice this plus, minus, plus. Those are the signs for row 1. Two, -2, -1. Those are my numbers. Those are my numbers from row 1. This, and this, those matrices are the cofactors, the submatrices, removing the row and column for each of these numbers. In general, you'll get more comfortable with it for a 3x3 doing it this way. For a 4x4 and bigger, typically you still write it out. There's just more numbers to deal with. Okay, so if I do this process, I end up with 2, -6 minus 3 plus 2, -4 minus 1 plus -1 or minus 1, -6 plus 3. If I do that number, I should have written it down from this morning. I didn't. Whoops. 2 times -9 plus 2 times -5 minus 1 times -3 equals -25. And note that's a plus. or this plus here, means that this negative 5 stays negative 25. So Nick, to answer your question, changing the sign depends on your grid. So your grid always starts with a plus in the 1, 1 location, and then it alternates. So plus, minus, plus, minus, plus, minus, and it goes on for infinity. Minus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, minus. So it depends on the size of your matrix. If you're doing a 3 by 3, these are the signs that correspond to each location. This is the 1, 1 location, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 2, 3, 1, 3, 2, 3, 3. If it's a 4 by 4, you just add another row, add another column. So you just have that grid in your mind. I typically write it down. So like row 1 here, I know it's a plus, minus, plus. I wrote it down. So I have a plus, minus, plus. Okay, then I want my next one. So that is the cofactor for just this one here. Then here I have another one. And my cofactor for 4, 1. Same thing. Remove the row, remove the column. My remaining elements are 2, negative 2, 1, negative 2, negative 3, 0, negative 1, 1, negative 2. The sign in front of that is a negative. This morning I forgot the negative. So make sure you keep track of all of the numbers you're working with. Okay, so the determinant for this matrix here, I'm going to use cofactor expansion along row 3. The signs on row 3 are plus, minus, plus. So I have a plus 1 times the determinant of negative 2, negative 3, negative 1, 1. Minus 0 times the determinant of 2, negative 2, negative 1, 1. Honestly, it doesn't really matter because I have the 0 there. Plus negative 2 times the determinant of 2, negative 2, negative 2, and negative 3. So this number is just the determinant of this matrix. It does not include my negative sign yet. So notice there's lots of places where you can drop something. Like I said, I dropped something this morning. And I mean, it didn't take that long to debug it. To figure out where I went, my calculation was wrong. But I also knew what my answer should be. Which you can always check what your answer should be with Matlab. We know the DET function. Okay, so I have 1 times negative 2 minus 3 plus 0 minus 2 times negative 6 minus 4. And this one should give me negative 5 minus 2 times negative 10. This gives me 15. So 15 is the determinant of this matrix, which means I need to apply my negative sign. So it's going to be negative 15. Benny, sure, absolutely. Write things down on a tablet. However, I mean, as long as you write them and you submit the PDF, that's fine. Doesn't matter how you write it. AP, yes, it is. These problems I find simpler and more straightforward than like Gauss elimination. I feel like there's less places to make a mistake. Once you get past a 3 by 3, it does become more complicated just because there's more steps. But just take things slow, one thing at a time. Okay, so I've got all of my cofactors. Now I can find... used too much space. Now I can find my determinant. So for this A matrix, my determinant is going to be 0 times C11, or 0, minus or plus 0 times C21, plus 1 times negative 25, plus 1 times negative 15, which this ends up being negative 40, which is what I get, or what I should get. You can always check your answers with Matlab. You just type in your A matrix. Yes, I did mean CLC. A equals 0, -2, nope, +2, -2, -1. 0, -2, -3, 1, 1, 1, 0, -2, 1, 1, 3, 2. Determinant of A, -40. So it helps when you know what your answer should be. It allows you to kind of double check what you're getting for all of your pieces. So like I said, I made a mistake this morning. I made a multiplication error. 1 times 1 is not 2. Who knew? So I made a mistake when I was calculating both of my cofactors, actually. So it helps if you know what your answer is going to be, because you can kind of use it to double check your math, but don't be afraid to write out each of your steps individually. Like you saw me write, this is my cofactor expansion for this entire matrix. If you want to still do it separately, like I did previously in this way, where I wrote each cofactor individually, feel free to do that. Sometimes that's easier. It helps you keep things straight. So don't be afraid to show lots of steps in lots of different areas, and then put things together at the end. There's a lot of signs, a lot of multiplications that can just be misplaced or done incorrectly. Okay. So, yeah. So like I said, this process works for any size matrix. Keep in mind, we are only talking about square matrices. Okay, you cannot find the determinant of a non-square matrix. Okay, and this process works for any size matrix. We could technically do this process for a 2x2 as well. We don't need to, though, because we have our little fish method. Yes, cofactors, they're just smaller determinants. Yeah, just smaller determinants. Okay, so cofactor expansion can be used for any size matrix. There is a shortcut, not a shortcut, there's an alternative method to find the determinant of a 3x3. I have it written in the notes. I think I call it the shortcut method, or diagonals. So there is an alternative method. This only works for a 3x3 matrix though, and essentially it involves diagonals again. It's kind of like an alternate version of our fish method. So for a 3x3, if we want to use the diagonals method, this is what it looks like. So we're going to take our matrix and we are going to write it next to that. We're going to essentially copy the values right next to it. So 1, -4, -2, 1, 5, 5, -4, 5, 5. And essentially, we are going to find a bunch of diagonals. So we're going to multiply a bunch of diagonals together. So starting in this corner here, we're going to take this diagonal, and this diagonal. So it's 1 times 5 times 5. My second one is 1 times 5 times -2. My third one is -4 times -4 times 5. We're going to add all those together. So we get 25 minus 10 plus 80. And when we do that, we get 95. So our first set of diagonals is 95. Okay, that's fine, that's fun. We're gonna do the same thing, but now diagonals going the other way. So now I'm gonna start here and then go my other way. So it's going to be 1 times 5 times 5, 1 times -4 times 5, and -4 times 5 times -2. And add all those numbers up. So when I do that, I get 25 minus 20 plus 40. Yeah, 40. When I add all those together, I get 45. And then I'm going to subtract my two numbers. 95 minus 45, which is 50. Which is the same answer I got using my cofactor expansion previously. Note, this is essentially the same thing as my fish method, where I take these diagonals minus these diagonals. I just have 3 diagonals instead of 1. And so this can only be used for a 3x3, but this is an alternate method for a 3x3. Anything else, we can use cofactor expansion. You'll get more comfortable as you go through. So, Michael, I completely agree with you. I really like this method. I find it to be more straightforward, less things to keep track of. However, the more comfortable I've gotten with cofactor expansion, I also see a application of that as well. So as you go through, you'll get more comfortable with one method or the other. You should know how to do cofactor expansion. Your homework will specifically ask you to do cofactor expansion along a specific row or a specific column. So you need to know how to do that. You need to know how to find your cofactors. Those show up a couple different ways. Once again, determinants, we will also use them to find the inverse of a matrix, which is, like I said, it's an easier way to do it compared to GaussJordan elimination. But you should get the same answer for a matrix depending on which method you're using. You should get the same answer. Keep in mind, this fish method, this alternative diagonal fish method that I'm coining, only works for 3x3s. So you can't do it for a 4x4, you can't do it for a 5x5, etc. Okay. I think I got everything. We're going to go ahead and stop there. On Wednesday, we are going to essentially look at properties of determinants and see how our determinant is affected, depending on how we change our matrix, and then we will solve a system equation. Yes, DM, absolutely. You will be able to use your calculator on the final. Do not be afraid of just pulling out your calculator and doing some basic math. You will also have access to Matlab on the final. Just keep in mind that the questions might not be phrased to where you can immediately use Matlab. You might be able to use Matlab maybe to see what your final answer should be, maybe, but it's not going to tell you how to get there. So absolutely, use your calculator. Absolutely. Nick, so our determinant, so that's a really good question. Let me pull up the examples again. So if we look at, let's go to Gauss elimination. So if we look at our different systems of equations for Gauss elimination, our final result for this one, this determinant exists. If we look at the determinant for this matrix, it's essentially going to be 1 times 2 times 1. The determinant of a triangle matrix is just the elements along the diagonal multiplied by each other. So this one has a determinant of 2. If your determinant isn't 0, that means your inverse exists. If your inverse exists, that means you're going to have a solution. So here it tells us that this determinant is 2, it's not 0, we have a solution, and you can see what the solution is. If we look at this one, this determinant does not exist. We cannot do a determinant on a non-square matrix. So it's not even the fact that it's not even the fact that it's going to be 0. It's just that we can't do it. So here's an example of where our determinant, we just can't do it, which means that we're not going to necessarily have one solution or a solution. Here we're probably going to have an infinite number of solutions because there's more unknowns than there are equations. So we can't really apply a determinant in this situation. If we look at the next one, if we look at this one, the determinant of this matrix is 0. It has a 0 row. Anytime you have a row or a column of zeros, your determinant is equal to 0. So for this final result here, our determinant is equal to 0, which means our system doesn't have an inverse, which means there's no solution. So you can see here, we break the rules of math. We can't move forward. There's nothing we can do with this system. So our determinant isn't necessarily going to be used explicitly on our augmented matrix, but we can use the determinant of our A matrix in order to determine if our solution is going to exist or not exist. And like I said, we will talk about that more in a couple weeks. If that made any sense to you, that's great. That means that you are following along. Couldn't you add the rows together to make the system work? But if you have, yeah, sure, you could say 0 plus 0, -4 plus 0, -4 plus 0. But if you have two rows or columns that are exactly the same, your determinant is still going to be equal to 0. So this system is set up in a way where this equation is just not possible. This last equation, it's just not possible. You can't have the right-hand side and the left-hand side work together. It just doesn't work. Yes. Okay. And same thing here. This determinant exists, therefore the solution will exist. Okay, with that, we're going to go ahead and stop. Like I said, we will look at row operations and see how they affect our determinant and some other properties, and then solve systems, which is an endless thing that we do in this class. So with that, I will take any final questions, and I will see all you guys later. Okay. See all you guys on Wednesday.